Alright everybody, this is section 10.3. This thing is very long and pretty complicated. What we're going to do is I'm going to try to go through it, I don't want to say relatively quickly, but pretty quick, and in class we're going to work on a bunch of these problems, okay? I need you to find your formula sheet, and on your formula sheet, if you flip it to what would be the top of the second page, the rest of those formulas is this section. So I'm going to try talk about it as we go down the line. And what's going to happen in your homework, there's 4 homework problems, because in every homework problem, you do every single one of these formulas. So that's why they're really long. Alright, so inferences on regression equations. We can make inferences on many different things. The population correlation coefficient rho, so basically your R value, but in the population form. And then also the regression line slope. And instead of just B, they have what they call beta. That's the Greek letter beta. So notice sample here, population there. R goes to P, A goes to alpha, B goes to beta. Your equation line goes to the Greek letters. Okay, so that's kind of what we're talking about within this situation. So the first thing we're going to do is sample test statistic, or testing the what? T-score for your rho, your R value, your correlation. Okay, linear correlation. All this is doing is testing to see if your correlation coefficient is significant or not. Alright? So there might be one-tail test, two-tail test, or different from. Okay, so obviously this is no different. The only thing is it's a P or rho. Alright? Your null hypothesis will always be equal to 0, and then you have your one-tail test. This is your t-score that you're going to use. Now they're going to give you the R value almost every time within your problem, but this is the crazy formula that we used in section 10.1. Alright, and then the end's obviously dumped right in there. So testing procedure, this should be very similar to the last chapter. Okay, so the null hypothesis is rho equals 0. You do your one or two tail test depending upon, you get a t-score, and you finish it. No different than you finished any problem on the previous chapter. So in this particular problem, suppose we've conducted a study to investigate relationship in years in school and the income. Okay, so I'm just going to move that and let you write it down. So we're going to test this claim at the 1% level. Alright, and we think that the more income you have, okay, the more years of school you have. We think there's a positive linear correlation. That's what we think. In the positive direction is how they state it. So all you do is dump this stuff in. So they got an R score, R value of 0.887, which I dumped in. N is 6, so I just dumped this in the formula, over 1 minus R squared. And you get a t-score of 3.84. What's different is your degrees of freedom is 4. So what you need to do is go to your t-table, or your blue chart, degrees of freedom 4, and 3.84 happens to fall between at the one-tailed test. See, it's a one-tailed test, 4 degrees, 3.84 falls between .005 and 0.01. So at the 4 degrees of freedom, 3.84. I lied, I'm one too far, aren't I? Oh no, I'm good. So 3.84 falls between 0.005 and 0.01. So is this significant? Do you reject? And we're comparing it to 0.01. It is less than. So we're going to reject the null hypothesis. Okay, so we reject that it's not equal to 0, and we say that there is enough evidence. And I'm not going to write this out because it's the same. There's a sufficient evidence to suggest that your rho, or your correlation coefficient, is positive. There's a positive linear correlation. That's what we want to write. Okay, so you need to include that as well. The next one, standard error formula. Now you need this standard error formula, this SE, over and over and over again with the rest of this chapter. So it's important that you understand kind of that this is a gateway into different things. So we talked about before the coefficient determination, the change, or the change that we know. is your y minus the y hats, and it's the distance from the regression line, things like that. This is the formula that shows exactly how much error there could be. So the more the data points are away, the more error that can happen. If all the data points land exactly on the line, your standard error is going to be 0 because there's no error. They're right on the line. You're not going to want this crazy formula. They give you the computational one in your formula sheet. This is the formula that you want to use. Okay? So on the next page, we're going to find the error of these data points. So that's going to be kind of the goal. So you could dump these into your formula, or your calculator. You know, X is in list 1, Y is in list 2. You're going to want to do that all the time, no matter what. And we're going to use the computational formula to figure this out. Now, in order to do that, there's a variety of things that need to happen. All right? So we need to find our... Now, if we go back to our formula, you notice in here you need an A and a B value. That comes from your least squares line. So basically, we need to do 10.2 first to find the A and the B value. And then we need to continue on and dump it in to find our error. So I'm going to kind of do this quickly. These other 2 slides just show you how to find the other 5 points, which you guys should know by now that you can use your calculator for that. And then you also need X bar and Y bar, or the averages of each. And then these come from the 2 variable stats from your calculator. And then to find your slope, okay, this should be straightforward from any other section that we've done. I'm not going to say too much about it. And then least squares line comes from 10.2. So you just dump in the y bar from the previous page, or the average of the y's, minus your slope that we just found. So this 0.5 just comes in. And then X bar happens to be exactly 40. So then you get an A value of 10. So your least squares line, that's supposed to not be there, would end up being that equation. Okay? So you need that equation, or the A and the B value, in order to find your standard error. So basically you're going to see this 10 and this 0.5 show up, okay, in here, because you need to know A and you need to know B. And then you need to know sum of y squared and so on. So if you kind of look at this, my standard error for this least squares line, the error that can show up, sum of y squared, the A value that we just found, sum of y, 213, the B value that we just found, sum of x times y over n minus 2. So you end up getting, here's my standard error. SE is how it's shown. So that's the formula that it's used. You're going to need your least squares line and use the methods that we used in class to find that. Now, what are we going to use this standard error for? Here's the rest of the chapter. Okay? There are going to be, I think, what, 1, 2, 3 separate types of problems in the next 10 slides. Okay? The first one's going to be a confidence interval for the y itself. And I actually don't have an example of this. I'm just going to do this example in class. But if you guys remember confidence intervals back in different sections, it was like x bar minus the error, and then x bar plus the error. That's what we're doing. We're going to build a confidence interval, except if it's asking for the y, the confidence interval for y, it's y hat minus the error. Okay, and we're going to do everything off of the y hat. And this standard error that we just found is what we're going to need for our error equation. Okay, so that's kind of the idea that we're going to use. I'm not going to show you because really it's not much different than before. What I want you to realize is this. The error for it, your critical value is going to be the same depending upon what they deem as their percentage level, and I'll show you that as an example in class. The standard error, this number right here, is what we just found. And then the rest of this junk, okay, is everything that is given to you in the problem. Alright? Given with the other things that we found with the B and the A and all that stuff. So I will go through an example of this in class just to save time. What I want to have on video are the rest of these. So I'm going to make an inference, and then I'm going to talk about regression and then confidence intervals for our slope. So the rest of this is going to be for our slope beta All right, and that's what we need to do. So standard error for the beta t-score, you should see this formula in the next one down. All right, and that's what I'm going to use and have an actual example of. So when we do this, if I'm going to test beta, this is how I find my t-score for a test. All right, and then they go through the same idea. How do you set it up? Null hypothesis. We're testing beta now is always going to be something equal to 0 in this chapter, and then it's the 1 or 2-tailed test, no different than chapter 9. Here's your t-score that you need to use as the formula on your paper, and then you finish it no different than any other test we've done in this class. Okay? I'm actually going to come back and do the confidence intervals so you're not all messed up. So what I want to do is I want to test, here's the data in the problem. They're going to give you some graphic or table or chart, and they're going to have an X and a Y. So X is the age of a volcanic island, and Y is the distance from the mid-oceanic ridge. Okay? And they want to test the claim. If you see a test, I need a t-score and I need a p-value and all that stuff. At the 5% level, if beta is positive. Okay? So if I'm going to test whether beta is positive, that's hinting at me that my alternate hypothesis is going to be greater than 0. Alright? So here is all the information you need to grab out of your calculator. And by now you've either been shown how to do this, or you need to do your second variable stats, or the other option that I will show you before. But you need all of these numbers at some point, be able to grab them. And then your B value you need, and then your standard error. If you dump all of these in, alright, the square root of sum of xy, or I'm sorry, sum of y squared, so the 2558.5 minus the a value, which is 7.072 times sum of y, which is 128, minus, I'm going to run out of room, and I knew I was when I set this up, the b value, which is 0.1721 times sum of xy, which is 8133. That's all on the top. And all that needs to be divided by n minus 2. Okay? So what you need to go back to is figure out what's your n. There's 1, 2, 3, 4, 5, 6, 7, 8 different things. So it's 8 minus 2. Okay, so that's how you plug in, and you should approximately get 6.5 as your standard error. So that's your SE. And using all of that information, here's how you set up your test. Okay? They expect the null to be 0 always. They claimed it to be positive, so my alternate is greater than 0. And then you need your t-statistic. Okay? So I'm going to move this down. And notice the b value, okay, is 0.171 or 21, which is from the previous page, divided by your error, which is what we should have received in that radical that I just set up on the previous slide. Sum of x squared is in here, the 30,203. And then 1 over, notice the 8 is just your n. That just goes on the bottom. It's almost easier just to say it's over n. And the sum of x is 415 squared. And if you do the complicated formula underneath the radical, take the square root, times it by that fraction, your t-statistic, or your t-value, is 2.46. And now this is where you go into your t-table. Once again, degrees of freedom is n minus 2. So 8 minus 2, you look at the 6 degrees of freedom, go over, and you find a t-statistic of 0.01 to 0.25. And what does that mean in the context of your problem? Okay, since it's less, you can reject, and basically you have evidence that the slope of the regression equation is positive. Okay, so it's less than our magical value, we reject, and that's how that works. So really the statistical testing part is no different. It's just you gotta realize, are they testing the slope, alright, or are they testing the R equation? And if you can figure that part out, it's not so bad. The last thing though is now going and building a confidence interval. So I'm going to back up a second. I know you guys are probably going to be annoyed that I should have just put this slide later. Okay, confidence interval for the beta or the slope. You got to read into the question, what are they asking, and then go find that formula. Okay, confidence intervals weren't so bad in Chapter 8 once you figured out what they were asking for. This b value is going to be the slope in your actual equation. All right, and then we're going to add and subtract the error. Here now is the error formula that we're going to use. Well, guess what? You know how to grab everything. T critical value. This is your standard error from that formula we did, hanging out all on its own. And then these numbers down here, we know how to find all of those. There's not much difference there. Okay? And then that's basically how you finish the problem. So if I go back and I want to find a 75% confidence interval for your beta. Alright? If that's what you want to do, we need to refresh our memory on how to find this confidence critical value. So you need to go to your T table. Alright, we want a 75% confidence level. And what's our degrees of freedom? 6, because it's always n minus 2. It was 8 minus 2 is 6. So if you go down to 6, and you go over to the 75 confidence level, now this is you have 3 lines on top of your page. You look in the bottom line for this pen is bad, 0.75, and go down. Wherever 6 is, see where they meet. That's 1.273. So that's how you find the critical score. And where does that thing go? Here's your critical score. And since it's the same problem, going off of that volcanic one, your standard error is just that formula that they found. So it's 6.5. And then these numbers are the same numbers you use over and over and over again. So your error ends up being about 8%. And then all that ends up doing is you add and subtract that from your actual slope. And that's what your beta interval is going to be, a confidence interval. We are what? 75% confident that we have an interval that shows the ocean floor is moving at a rate of 8 to 26 millimeters per year, because that's what beta is talking about. That's how far it's moving. It's the slope, the rate of change. Okay? So I know that's a lot of things to get through. I know that seems like a lot of information. But if you kind of follow through, and if you look at some of the problems, which we'll do one in class, you're going to find there's multiple different levels for each part. You're either going to test the R, or the rho, or your correlation coefficient. You're going to find a confidence interval for Y. You're going to test the slope for the B, or the slope. And then you're going to find a confidence interval for the slope. So you're kind of tying Chapter 8 and Chapter 9 all together into linear regression and talking about the slope and the correlation coefficient to see if they're significant. Okay? So that's what this section's all about. There's one quick example. We're going to do this assignment over the next day or two, and hopefully that wasn't overly painful. You guys have a wonderful day.